All right, this is our last lesson of this unit. It's our last rule we're going to learn. It's called the chain rule. And I have three functions up here. I wrote a lot on the board. You don't have to copy things down, but I just kind of want you to understand what's going on here. We have J, H, and K. And they all have something in common. All three of these are compositions of two functions. Okay? Now, I asked if we could take the derivatives of these three functions. Well, the first one I could, right? Because I can simplify 2x squared plus 3, I could distribute it, and then take the derivative. Done. So I can take the derivative of this composition of functions. H and K are different. H, it would take me a very long time to distribute 4x cubed minus 3x squared plus 2x to the fifth power. And I don't have that kind of time to distribute then take the derivative. And K, I just can't. Because I can't distribute things when you have the square root of something does not become the square root of 5x to the fourth plus the square root of 3. That is not correct. So I'm just stuck. So I need a new rule that can take the derivative of all three of these functions, but primarily I would use this new rule for H and K. Okay? And what do I mean by a composition of functions? Well, we have kind of an outside piece to our function J, this kind of quantity being squared. I'm going to use parentheses. However, you can think of the outside function being x squared, and the inside function is the stuff inside the parentheses, here 2x squared plus 3. And if I compose these two functions, I plug g in for x, we get f of g of x, which is what J is. Okay? Mr. Russell.
How come when with the square root you can't do 1/2, like on the 5x to the 4th?
I could, but it's still not correct. If I took the square root of two numbers that are being added together, let's take I don't know, like 15, and let's get a perfect square here, 9. So 5 and 4, the square root of 5 plus 4. We know that's going to be equal to the square root of 9, which is 3, right? 3 is not the same as the square root of 5 plus the square root of 4. The square root of 5 is some decimal between 2 and 3, and the square root of 4 is 2, so we have 2 plus some decimal between 2 and 3. That's not equal to 3, right? So even if it's to the 1/2, it's just not going to work. Okay? So we need a new rule. Here's how we understand these compositions of functions. We have this thing to the fifth power, or f of x. The outside function is this x to the fifth power. And then we have the stuff on the inside. We're going to call the f of x's here the outside functions, and the g of x the inside functions. And if I want to take the derivative of this composition, this outside and this inside, here is the rule that I will use, the chain rule. The derivative of a composition of functions with an outside function and an inside function is equal to, and you can see the proof of this in your book or online, proof of chain rule, and they'll show you. Take my word for it, though. The derivative of this is equal to the derivative of the outside, or f prime. I'll write it as d dx out. Leave the inside alone. So it's almost like change the outside, leave the inside. And then we multiply by the derivative of the inside. Okay? Watch how I can take the derivative of all three of these functions now using this rule. Okay? First, just to make sure you know that the rule works, I'll show you that it will work with j. We already know what the derivative of j is. When I distributed j, I got 4x to the fourth plus 12x squared plus 9. I took the derivative, I got 16x cubed plus 24x. By taking this and denoting it as an outside and an inside, I can use the chain rule. Well, what I like to do and what I recommend my students doing is to write down what's the out and what's the in. And I'm okay if you use the parentheses as being, you know, hey, this is the outside, this stuff being squared. And then the inside would be the 2x squared plus 3, the stuff inside the parentheses. Using the chain rule, here's how I would get the derivative. I would take the derivative of the outside. Well, what's the derivative of stuff being squared? Well, think about it as an x being squared. If you thought about it as an x being squared, the derivative of x squared is just 2x to the first using the power rule. So I would say this is 2 my stuff to the first. That's the derivative of the outside. Leave the inside alone times the derivative of the inside. And that's j prime, sorry. Okay? Now, let's see, is that derivative the same as the derivative that I found by distributing? Well, I can simplify, I can multiply the 2 and the 4x, I get 8x. I can take the 8x and distribute it into the parentheses. I'd get j prime is equal to, this is fully simplified, 16x cubed plus 24x. And I go up and check with my original derivative through distributing, and I get 16x cubed plus 24x. Okay, so the chain rule works. And I don't have to use the chain rule for j, though, in the future. Okay, but I'm just showing you now you have two different ways to take the derivative of that. You will have to use the chain rule for h and for k, functions like that. So let's take the derivative with our new rule of h and k. I'm going to shrink this part first, and we'll do it together. First thing to do, write down what's your outside, what's your inside. I'll do that for you this time. Sound like a piano. Then, using your chain rule, we'll take the derivative of the outside, leave the inside alone, times the derivative of the inside. The derivative of the outside, if you think about it, is like x to the fifth. The derivative of x to the fifth is 5x to the fourth. So we will go 5 stuff to the fourth. You can fill in your stuff. Sometimes you might want to just go straight to your derivatives first and fill in the stuff later. You can go 5 stuff to the fourth times the derivative of your stuff. And then you can go back and say, oh, I got to take and plug in what was my stuff, the inside, which was my 4x cubed minus 4x cubed minus 3x squared plus 2x. Okay? And that's correct. Can we simplify this one? Well, I'm not going to expect you to have to take this and take it to the 4th power, no. But maybe you'd be expected to take this 5 and know that you could distribute to the 12x squared, the 6x and the 2, but know that you can't distribute that 5 to the stuff being taken to the 4th power, because that exponent would take precedence over the multiplication of the 5. So maybe for a multiple choice question, you'd be expected to rewrite this way. Something like that, okay? That's just taking this 5 and distributing into here, here, here. Okay, why don't you guys find the derivative of k? See how you do. Check your answer with a neighbor. Help your neighbor if he was taking the quiz. Just use the rule if you haven't done it yet. Derivative of the out, leave the in, times the derivative of the in. We know that the square root should be the same as something to the 1/2 power. Once we get that, we can go. This would be the derivative. It's the correct derivative. You could simplify this, however. The 1/2 could be multiplied by the 20x cubed, and this stuff to the negative 1/2 can be turned into the positive 1/2 power and put as a square root symbol instead of a 1/2 symbol. Okay? Any questions? Now, I will tell you, and I've told you in the past, that simplification usually is not that big of a deal, especially with the product and the quotient rule problems that you had for your homework. I find that when you are asked to simplify, it is typically with problems where you have to take the derivative using the chain rule. So I find that on quizzes and on tests, you will have to know how to write k prime as this, because you will see this as your multiple choice answer choice that you will select. And h prime, you will see this instead of the previous one. Okay, so be prepared to simplify for these derivatives. And you should attempt to practice simplifying using on your homework. Okay, moving forward. We might have something involving multiple rules. This example over here on the left, this is an atypical example where taking the derivative is actually not too difficult, but it's a simplification process that will be expected of you where a lot of people make mistakes. Now, first thing, we got to know what we're dealing with. We have x squared times 2x cubed minus 3 to the 4th power. We should know just by looking at this that I cannot distribute this x squared into those parentheses, right? Order of operations says I'd have to take that stuff to the 4th power first before I distribute that x squared. So this is out. Can't do that. Instead, what we have here is just what it is, which is a product of two things. And if I want to take the derivative of it, I need to use the product rule. We have the first guy and the second guy. We will have to use the chain rule to take the derivative of the second guy. Question?
If that x squared was like a 2, would you just say without parting outside?
Yes, excellent. If the x squared was just a 2, was it a constant? You could just put that as part of the outside as 2, the parentheses to the 4th.
So if it's a variable, then you have to use like the product or
Yeah,
rule. If
because
you're
it's
plugging stuff in,
uh-huh.
if they give you a constant, then do variables not like if they give you stuff to plug in, then they become constants, right?
Well, if I ask you to find y prime of 1, you still have to find y prime first using the product rule. Okay? Okay. And same thing, if I gave you numbers to plug in, you still cannot distribute that number in there. Still not good. Okay. Good. So let's go. Let's find this derivative. Well, derivative of the product will be the derivative of the first times the second. Plus the derivative of the second. I'm going to do this up here just so that we are comfortable with it. We have an out, which is the stuff to the 4th power. We have an in, which is the 2x cubed minus 3 stuff. The derivative would be the derivative of the out for the stuff cubed. Leave the inside times the derivative of the inside, which is that 4x. Okay, so I'll write it down here with the inside left in. For the stuff cubed times the derivative of the inside. The derivative of the inside, I'm sorry, is not 4x. This is 2x cubed. This would be 6x squared. My apologies. This is 6x squared. So that is just the derivative of g. I need to multiply that by f. So this is the derivative of the first times the second piece. This is the derivative of the second piece times the first. Don't forget to multiply by the first in the end, okay? And this is correct. This is the correct derivative. You could plug in x values and find out your slopes of that y equals equation. However, this is an atypical problem where they will ask you on a multiple choice question to take this derivative, and you'll get the derivative just like I got it like this, but you will not see this answer on a multiple choice selection. So this is when you need to be prepared to work our way down to a simplified answer, which you will see as an answer choice. Okay? Here's how we're going to simplify. Whatever you have that can be multiplied together in each term, and it's important to see that you have two terms multiplied together. So for the first term, I can't multiply the 2x by the stuff in the parentheses getting taken to the 4th power. And over here in this term, I do have the 4, the 6x squared, and the x squared, which would be 24x to the 4th. Okay. The next step will involve factoring. We will factor out our common terms. Now, I teach my algebra students when I introduce them to factoring that, distributing, they first learn distributing, and distributing is just multiplication. Factoring is just division. It's important to see that you have two terms. I'm just going to write up these two blue lines as this is what I'm dividing out, okay? But it's important to see that you have two terms separated by addition. Even though these terms include products, there's still two terms. We will be able to divide out whatever these two terms have in common. Well, they both share a 2x. There's a 2x here. There's 24x to the fourth. So I could divide out at least a 2x. But they also share in common a 2x cubed minus 3 cubed. This has 4 of them. This has 3 of them. I can pull out a 2x cubed minus 3 cubed. And sometimes it's easy to see if you write factoring out as a division process what your ending product is going to be. You're going to divide out this. So we'll have y prime is equal to 2x times 2x cubed minus 3 cubed. That's what's been divided out. And what you have left over, it goes in parentheses with your addition symbol in between. Well, after I divide out 2x times 2x cubed minus 3 cubed, I'll just have a 2x cubed minus 3 to the first, because these 2x's will go away, and these 4 would cancel with these 3, leaving me with just one of those. So I just have 1 2x cubed minus 3. I can write that to the first power if I want to, or I don't need it. And then after I factor this out, these 2x cubed minus 3 cubes will cancel with those. And then I'll turn into 12 when I go 24 divided by 2. And instead of x to the fourth over x, it'll be x cubed. And then the final step would be to simplify the stuff inside this that you can. I have 2x cubed plus 12x cubed. Those are 14x cubes. And this would be an answer choice on a test, on an AP test. It might even be one step further, and it might be with the 2x distributed in here to make this 28x to the fourth minus 6x. Might be like that. Okay, but this is what you need to be prepared for in terms of simplification. The AP test, I've never seen the AP test use trig identities to simplify things. Maybe there's a sine squared plus a cosine squared, which is equal to 1. Maybe they've used that once back in the day, but I haven't seen that. Where they do ask you to simplify are things that are algebraic in nature, polynomials, not trig functions, okay? So prepare yourself for that. You might see something that involves the chain and a quotient rule. I'm not going to do this, but prepare yourself to do, 5, the stuff to the fourth, and then use the quotient rule for the derivative of your inside. Okay? We're going to move on now. Because typically, we will see trig functions that have a composition involved. These are 2 trig functions where compositions are involved. And the question is, what's the difference? And there's a huge difference. And the huge difference is, where do the parentheses go? And the huge key to dealing with trig functions that are compositions are to use parentheses. Because the sine squared of x is written with parentheses as the sine of x quantity squared. But the sine of x squared is written as the sine of x squared. Now, it's very important with trig functions that you understand that we are not having a product here. This is not sine times x squared. It is the sine of x squared. It's always a trig function of an angle to make it correct. So it's not sine times x squared, it's the sine of x squared. This is sine of x, quantity being squared. Now you'll see on your homework tonight, and I'll show you a couple examples where you might get confused, that the parenthesis location sometimes is not obvious what to do here. Like if you look at 42, you see y equals the sine of pi x. This would be the sine and then parentheses around the pi and the x. You might want to write that down. It's not the sine of pi times x. It's not obvious, but I can see how people make mistakes with that. This is the sine of pi x. You see y equals sine pi x. Assume it's y equals sine of pi x. Okay? Something like this, the sine of pi x squared, since the squared is there, it's the sine of pi x squared in parentheses. Sine of pi x squared, written like this, you can rewrite it as the sine of pi x squared. Okay, see how that works? Very, very important to see and to know how to rewrite these. This is the cosine squared of pi t, so we'll talk about when we have 3 compositions. Yes?
So is it to assume that anything's being times, but the sign is in the front and not in the back where it'd be confused?
Good point. If you want to multiply something by the trig function, you will normally put it up front. Okay? So this is just notation heads up. All right, let's go back to it. The key to using parentheses and understanding the differences is that these have different outsides and insides. In this situation, the outside function is the x squared, the parenthesis being squared. The inside function is the sine of x. Here, the outside function is the sine of x, and the inside function is the x squared. So when you're taking your derivatives, you're starting with 2 different outside functions. You're going to get 2 different derivatives. And that's our next step, is to find the derivative of these 2. Okay, go ahead and do it. See what you get. Yes, sir. Both of them. Check your answer with your neighbor. Remember, derivative of the outside, leave the inside alone, times the derivative of the inside. That's it. Not difficult. I guess I kind of should have made this outside make a little bit more sense by doing it the sine of stuff. Okay? We should see the differences. In this one, I took the derivative of the stuff being squared to stuff to the first power times the derivative of the inside. Here, I took the derivative of the sine first, which is the outside. I got cosine of x squared times 2x. Okay? Let's look at 2 ones using secant. I want to get rid of this tangent. Let's get rid of, have secant cubed of x, and let's have the secant of x squared plus 4x. There. go ahead and find the derivatives. The first thing I would do is to rewrite using parentheses, as many as I can. This would be y equals the secant of x quantity cubed. And that would denote that my outside is the stuff being cubed, and the inside is the secant. When I take the derivative of the outside, leave the inside alone, times the derivative of the inside. We should remember it's secant x tangent x. Okay, and then fill in the inside as you see fit. Okay, for the other one, the outside is the secant. And the inside is the x squared plus 4x. Well, we know the derivative of secant is secant x tangent x, right? It's not the derivative of secant, it's the derivative of secant of x. The derivative of secant of x is secant x tangent x. Here, the derivative would have to be the secant of your stuff times the tangent of your stuff. And then you would multiply that by the derivative of that inside. So all of a sudden, it'd be the secant of x squared plus 4x times the tangent of x squared plus 4x times that derivative of 2x plus 4. Okay, so that's something to keep your eye out for. We might have a composition of 3 or more functions. Let's look at this one first. Definitely copy this one down so you can see how it works. If I rewrite this function using parentheses, we will note and be able to see that I have 3 things going on. Of the sine of 4t squared all being cubed. Now here's what we would have to do. Work outside to inside. The outermost piece is the stuff being cubed. The parentheses cubed. The next piece is the sine of stuff. The last piece is the 4t squared. If you have 3 or more functions being composed, you treat it almost just like 2 functions. You just work outside in. If you want to write down something with a third function back in your rule, I'll show you. F of g of h of x. It would be the derivative of the outside, leave the inside of that alone, times the derivative of the next outermost piece, leave the inside of that alone, times the derivative of the innermost piece. It just goes from outside in. F prime, leave it alone, times g prime, leave it alone, times h prime. So let's see what this derivative is going to look like. This is what I kind of sometimes don't like to fill in the stuff until the end, I'll just use a bunch of parentheses and then fill it in at the last second. The derivative of the outermost piece will be 3 stuff squared. The derivative of the next piece, cosine. The derivative of the last piece, 8t. And then fill in the gaps. This would go in here, and this would go in here. But it's not the sign of the parentheses, it's the sign of 4t squared. And this would be the 4t squared. I'll show you this on the video. This is 4 different functions being applied together. And it'd be a long derivative, but you can do it. Okay, I'll show you that on the video. We're going to finish off talking about table problems. And there's an easy one, and there's a tough one. The first one is an easy one. The second one is a tough one. I gave you a bunch of information, and I give you f of g of x, find the derivative when x is 2. We should know now the rule for the chain, the composition of functions, that the derivative of f of g of x is just f prime of g of x times g prime of x. The only thing that is a little bit different on these is when I need to find this at 2, it'd be f prime of g of 2 times g prime of 2. Well, watch what happens. I know g of 2 and g prime of 2. G of 2 is 3. G prime of 2 is negative 2, so I got negative 2. I'd have to find f prime of g of 2 to finish off this answer. So that composition means I got to work inside out to find the value. F prime of 3 is 4. So I got 4 times negative 2, which is negative 8. And finally, going to the problem where most students get the incorrect answer, something like this. Take the derivative of g of x cubed when x is 2. Well, everybody says that the derivative of g of x cubed is 3g of x squared. Because that's the derivative of like something being cubed, right? But this is incorrect. Because we're missing something. And what are we missing? G prime of x. This has an outside and an inside. Everybody write this down as a super common problem that everybody gets wrong that you probably will see on your test. You have an outside, which is the stuff being cubed, and the inside, which is the g of x. You take the derivative of the outside, leave the inside, times the derivative of the inside. When you plug in 2, you can then use your table to find the values. Yes, sir.
How do you apply the rule for some f of x?
Like here with g of x?
But don't you need an f and a g?
Well, this is still a composition. The f of x is the quantity being cubed. That's the outside, and that's the inside. Outside, inside. Derivative of the outside, leave the inside alone, times the derivative of the inside.
But like, on all those, I want to get like f g of x inside of it.
Right. This outside is what we call the f of x.
We just treat it as an f of x.
Yes, we treat this as the outside function. I could have changed this to
So since it's inside
f right here.
something else,
Yep,
we know there has to be a function outside.
exactly. Since it's inside something else,
There has to
that it's a composition. There is an outside function. Okay, we could do like that too.
be. So that you don't have to show the outside function, it's imply when there's something else inside.
Well, I just showed it right here. The outside function is this being cubed. Okay, I'll do a couple more problems on the video. Okay, going back to the composition of 3 functions, let's go back to this. This is another repeated application guy. Let me shrink this. Key to understanding things is what is my outside, what is my inside. This is 1/4 sine all of 3x plus 2 to the 5th. That sine is all being squared. Yep. All right, so I'm going to list out my outermost all the way to my innermost. My outermost would be, and I'm going to include the 1/4 there, the 1/4 stuff being squared. Then is the sine of stuff. Then it's the stuff to the 5th power, and then it ends up with the 3x plus 2, going all the way from out to in. If we want to take the derivative, we just start from the outside. Now the 2 gets multiplied by the 1/4. You subtract 1, you just get 1/2 everything that's in there. Then the derivative of the next piece would be the cosine of whatever's in there. Then the derivative of the next piece would be the 5 stuff to the 4th power. And then we finish off with the derivative of the last piece, 3. What goes in here? The sine stuff goes in here. This goes in here, that goes in there. If I want you to show it, this is what it would look like. 1/2 sine squared, nope, no, not sine squared. Sine of 3x plus 2 to the 5th. The cosine would be of just 3x plus 2. No, it'd be 3x plus 2 to the 5th. And then this would be the 3x plus 2. Okay? You work outside the in, no big deal. That's fine. Here, table problems, same deal. I will show you this guy. We want to find the derivative of the square root of f of x. It's very, very important when we have this to denote that you have an outside, which is the square root, which can be written as this to the 1/2, and the inside, which is the f of x. So if I wanted to take the derivative of this, I'd have the derivative of the outside times the derivative of the inside. Well, that's 1/2 f of x quantity to the negative 1/2 times f prime of x. You can then plug in 4 and figure out what this is equal to. See, f prime of 4 is negative 1. F of 4 is 7. So we need 1/2 7 to the negative 1/2 times negative 1, or negative 1 over 2 root 7. Okay. I'll show you this. If you have f of g of x, when x is 1, we'd have f prime of g of x times g prime of x. Plug in 1 everywhere. And here's important. We'd have to find g of 1. G of 1 is 5. And then we'd have to find f prime of 5, whereas g prime of 1 is down negative 1/2. The slope of g at 1. F prime of 5, the slope of f at 5 is negative 1, so this becomes positive 1/2. Okay, so be ready for those. Finally, what we can do now using the chain rule, if we want to do, is rewrite functions knowing that this is 1 over x plus 2 to the first in the denominator. I could rewrite this as x plus 2 to the negative first in the numerator. And after I do this, I'm able to use the chain rule with an outside and an inside to find the derivative a little quicker than if I did this using the quotient rule. Same with this. This would be negative 3 over 3x squared plus 2 to the negative first. And I could rewrite it if I wanted to as negative 3, sorry, this is to the positive first, but negative 3 times 3x squared plus 2 to the negative first. And just to show you what this would be, the derivative of the outside would be negative 1, the inside to the negative second, times the derivative of the inside, which is just 1, giving you negative 1 over x plus 2 quantity squared. Okay, maybe that's easier than using the quotient rule for this. I don't know. It's up to you. Here, this derivative, the derivative of the outside again, the negative 1 being multiplied by the negative 3 being 3. The stuff to the negative second. And then the derivative of the stuff is 6x. So rewriting that, we would get 18x over 3x squared plus 2 squared. Okay. Same process could be done if you have something like this. You can rewrite it as negative 3 times negative 2x plus 5 to the negative 4th. Use the chain rule. This, it probably is either way difficult. It could either be a quotient rule because you'll have the 2x. If you move this up, you'll have a product rule. Okay, but that's it. I hope we understood this lesson. Thank you.